So what's the real difference between a programmer who's doing okay and a software architect who's absolutely crushing it? Well, today, we're going to unpack the high-level concepts that make up that difference, the ideas that top engineers are getting a handle on right now to build the future. You've probably thought about this. It's at the core of growing your career in tech, right? You see two developers, both super smart, but one of them is just on a totally different level, career-wise and salary-wise. So what gives? It's almost never about who can type code the fastest. The real answer? It's about a different way of thinking.
And that right there is the key. The big leap in your career happens when you go beyond just writing lines of code and you start to understand the whole system. We're talking about the high-level principles that make software scalable, reliable, and, intelligent. It's all about learning to think like an architect.
So how do we get started? Well, we've broken down 9 key concepts into 4 main themes. We're going to kick things off with the new AI stack. Then we'll get into how to build for a worldwide audience, then how to make your apps practically bulletproof, and finally, we'll take a little peek into what's next for the web.
First up, AI. You know it, I know it, it's completely changing the game. And for engineers, that means we have to master a whole new set of tools that go way, way beyond just typing a question into a chatbot. So, at the very heart of this revolution are large language models, or LLMs. You've definitely used them. Think ChatGPT. These things are trained on just a mind-boggling amount of text from the internet, which lets them understand and generate language in a way that feels incredibly human. But here's the thing, just using them isn't enough anymore.
The real value, where you as an engineer can really shine, isn't just in using an LLM, it's in customizing it. It's knowing how to fine-tune a general model so it's perfect for a specific task. It's figuring out how to make it work safely and securely with your company's private data. And it's learning how to engineer prompts to get exactly the right result, every single time.
And that leads us to a huge, huge problem. Let's say you ask a public LLM to summarize your company's sales report from last quarter. Well, that model has no idea what your sales data is, so it might just make something up. This is what we call a hallucination, and for any serious business, that's an absolute deal breaker. So, how do we fix this? With a really clever technique called RAG, which stands for Retrieval Augmented Generation. Okay, so instead of asking the LLM directly, your application first retrieves the correct sales data from your own private database. Then it augments the prompt. It's basically saying, hey, LLM, using only this data I'm giving you, please summarize the sales. And finally, the LLM generates an answer that is based 100% on your actual data. No more making things up. Problems. Okay, so we've got an intelligent system. Awesome. Now, how do we make sure it's fast and available for everyone on the planet? That brings us to our next big idea, architecting for a global scale. Your users could be anywhere, and your app has to feel zippy for every single one of them.
This slide really shows the problem that edge computing solves. Imagine your main server is in Canada, but your user is in Libya. Every single click has to travel halfway across the world and back again. That delay, what we call latency, is what makes an app feel slow and clunky. Edge computing fixes this by putting smaller servers at the edge, much closer to your user. So that request from Libya gets handled by a local server, and boom, everything feels instant.
All right, next up is a concept you've probably experienced a million times without even realizing it, event-driven architecture. Think about ordering food at a busy fast food place. You don't just stand at the counter and block the line while they make your burger, right? No, you place your order, you get a number, and you step aside. When your food's ready, they call your number. That's the event. And you go pick it up. This system is super efficient because it lets the kitchen handle tons of orders at once without getting stuck. Software can work the exact same way. Okay, let's talk about money. In the old days, you'd rent a server by the month or by the year. But what if you're running a massive Black Friday sale that only lasts for one day? You need a huge amount of power for those 24 hours, but for the rest of the month, those expensive servers are just sitting there, doing nothing. It's like renting a giant stadium for a full month just to host one 4-hour concert. It just doesn't make sense. And this is where serverless computing comes in and changes everything. Now, the name's a little misleading. There are still servers involved, of course, but you don't manage them. You just give your code to the cloud provider, and they run it for you, billing you only for the exact milliseconds it's actually running. It scales up instantly when you get a flood of traffic, and it scales down to 0 when things are quiet. The bottom line is, you stop paying for servers to sit around doing nothing, which can save you a ton of money. So, we've built a smart, global application. But is it reliable? Is it secure? Our third theme is all about the stuff you absolutely cannot skip. the principles for building professional systems that your users can actually trust with their data. This quote, it perfectly sums up the modern approach to security, and it's called zero trust. The old way was like building a castle with a big wall and a moat. Once you were inside, you were considered trusted. But that model is totally broken now. I mean, what happens if an attacker gets inside the castle walls? The zero trust philosophy flips the whole thing on its head. You start with the assumption that you've already been breached. It means you don't trust anyone or anything by default, not even requests coming from inside your own network. Every single request from one internal part of your system to another has to prove who it is and what it's allowed to do. My right hand does not trust my left. You verify everything, always.
Now let's talk about reliability with another super simple analogy. When you're waiting for an elevator, you press the button. If you get impatient and mash that button 10 more times, what happens? Nothing different, right? The elevator still just shows up once. That property is called idempotency. An operation is idempotent if doing it once has the exact same result as doing it 100 times. And this is absolutely critical for things like online payments. If a network glitch makes a customer hit the buy button twice, you'd better make sure they only get charged once.
And when things inevitably go wrong, because let's be honest, they always do, how do you figure out what happened? You do it through observability. It's all about being able to understand what's happening inside your system just by looking at its outputs. And it rests on three main pillars. You've got logs, which are like a diary of every single event. They tell you what happened. Then you have traces, which follow a single request on its journey through all your different services. They tell you where it happened. And finally, you have metrics, which are your high-level vital signs like CPU and memory usage. They tell you how the system is performing. With these three, you can solve just about any mystery.
All right, for our final theme, let's look at a technology that is just blowing the doors off what we thought was possible inside a web browser and pushing its limits like never before.
That technology is WebAssembly, or WASM for short. For decades, if you wanted to run code in a browser, you had one choice: JavaScript. That was pretty much it. WebAssembly completely changes that. Think of it as a new, universal language for the web that's incredibly fast and efficient.
So why is this such a big deal? It all comes down to performance, pure, raw speed. It means you can take code that's written in super fast languages like C++ or Rust and run it directly in the browser, almost as fast as if it were a desktop app. This unlocks the ability to build incredibly powerful, complex applications that run entirely on the web. You've used it. Think about how insanely complicated something like Google Sheets or the web version of Microsoft Teams is. That level of power in a browser, that's made possible by WebAssembly.
And there you have it. We have just put together a brand new architectural toolkit. We've covered how to build smarter apps with LLMs and RAG. We've learned how to go global with edge computing, event-driven architecture, and serverless. We figured out how to make our apps rock solid with zero trust, idempotency, and observability. And we took a look at the high-performance future of the web with WebAssembly. These, right here, are the building blocks of modern software.
You know, we started this whole thing by asking what really separates a good programmer from a great architect. And the answer is understanding these principles. So the last question isn't for me, it's for you. Now that you have this toolkit, how are you going to start bridging that gap and thinking like an architect? Thanks for joining me.